はい、もう始まってます。
Yes, so time has come, and I'd like to open the webinar. Good evening and good morning, everyone. My name is Naoshi Ueda from Kansai University, and I'm one of the organizers of this webinar. And I will be serving as today's moderator. First, I'd like to express my gratitude to you for joining this webinar, Frontier of Concrete Technology. This is our 7th webinar. Today's topic is 3D concrete printing. So today, we are going to welcome two leading researchers in the field of 3D concrete printing, Professor Victor Michelin from Germany and Professor Minoru Kunieda from Japan. They will provide us with advanced insights to 3D concrete printing. Each researcher will deliver a 30-minute presentation. So this is the schedule for today's webinar. First, I would like to introduce the Japan Society of Civil Engineers, JSCE, and the Concrete Committee within JSCE, because this webinar is organized by the Concrete Committee of JSCE. Following that, Professor Victor Michelin and Professor Minoru Kunieda will each provide us with their research presentations. We have also scheduled a short Q&A session after each presentation. After their presentations, we will have a panel discussion with both professors. So let me introduce the JSCE and the Concrete Committee now. The Japan Society of Civil Engineers, JSCE, has a long history of more than 100 years. It is also the one of the largest society in Japan, with about 40,000 current members. JSCE is now focusing on international activities and promoting them worldwide via its webpage and social media. JSCE has several research committees. The Concrete Committee, to which we belong, is one of these research committees. This webinar is one of the activities organized by this committee. The most important activity of the Concrete Committee is to publish the standard specification for concrete structures. The latest version was published just last year, and part of the specification has been translated into English. Currently, you can freely download it from the Concrete Committee's webpage. The Concrete Committees are also focusing on international activities. We issue a newsletter every 3 months to inform about our latest activities. Moreover, we hold an international web seminar every year, primarily with Asian countries. This year, we are planning a seminar in Laos. And then, as I mentioned before, today's webinar is our 7th webinar, meaning we have had already 6 webinars up to now. You can watch the past webinars on YouTube. Please search for JSCE and Frontiers of Concrete Technology if you are interested. And before we move on to the first presentations, let me announce a few important notes. During the presentations, you might have some comments or questions. When that happens, please use the Q&A box located at the bottom of the Zoom window, as shown here. Please remember to include your name and affiliation with your comments and questions. Some of the questions and comments will be responded from the invited researchers. So let's move on to the main portion of our webinar. Now, I would like to invite Professor Victor Michelin to be our first presenter. Prior to his lecture, I would like to briefly introduce Professor Victor Michelin. He has been the director of the Institute of Construction Materials at Dresden University of Technology in Germany since 2006. He is a member of both the German National Academy of Science and Wilson Medal Engineering and the Science Academy of Saxon. He is a Leyland Fellow and has been honored with the Wilson Medal for Materials Research by the American Concrete Institute and Innovation Awards from both Werner and FIB. Professor Michelin is also editor of journals Cement and Concrete Composite and Materials and Structure, as well as chair of Leyland technical committees. He is also a member of several research committees. And today, he will deliver a lecture entitled Large-Scale Point Printing with Ready-Mixed Concrete. So, Professor Michelin, please share your slide and start your presentation when you're ready.
So thank you so much, Professor Ueda. I need the rights to present, so if you can assign it to me, so then I will be happy to share my screen. So
Okay.
you can see my screen, right? Yeah. Okay.
Yeah.
Thank you so much. Now it works. Okay. So let me start. So yeah, welcome from my side to this webinar, and thank you so much, Professor Ueda, for inviting me to give this little presentation. I will focus today on a specific type of 3D printing, which we call large-scale monolithic printing with ready-mix concrete. So actually, it's a lot of information already in the title. But before going deeper into this topic, I would say a few words why we are dealing with 3D printing at all. So why is this topic interesting for us, for the industry, and why this topic is developing very fast? So obviously there are some driving forces behind, and the first point I want to address is the geometrical freedom. Indeed, using this technology, we can produce pretty complex geometrical forms without much additional effort, which in case of casting is not feasible. So the second point is we can use this geometrical freedom also to optimize topology. It means that we can go into the structural design following the principle form follows force, and we can spare material, so we can also provide some additional functionalities. For example, if we talk about construction physics or similar points, so we can combine here load-bearing capacity maybe with some other additional functions like thermal insulation, for example. Here are some examples. You see here we can produce slender structures with little material, but with a good load carrying capacity. And in the case of the wall, it's also additionally capacity to insulate a little bit against heat or cold. The next point is it's about productivity, and this is, I think, even more important point. In most of the countries, the productivity in construction is kind of stagnating. In other branches, it's developing pretty fast, but in construction, it's more or less on the same level as in the last decades. And it's mostly because of high portion of manual labor. And also we actually have less and less skilled labor on the construction side. So it's also difficult to find a replacement for the people who retire. So it's additional motivation to use robots, machines. And given the fact that price for such robots go down while the salaries for the labor go up, so the motivation is increasing. So we are kind of interested in using this technology more and more, also from the economical perspective. And finally, this is the last slide for the motivation. For us, it's clear that digitalization is the way to move forward. In planning, we already use digital tools like CAD and BIM pretty successfully, so it's kind of already established. But what happens then with this planning data? We go more or less in the conventional manner. So we have some printouts, so 2D plans, and try to reconstruct from the 2D plans 3D buildings. So I believe much more efficient if you send this data from planning directly to the machine, so from digital planning directly to digital fabrication without any loss of data. And of course, it would also make the entire process more robust and efficient. Good. So this was a little introduction, and now I want to address one of the technologies which is widely used in 3D printing nowadays. It's extrusion-based concrete 3D printing. So we use here extrusion as a key component for shaping the filaments. There are some other techniques which exist as well, like spraying. But today I really concentrate only on extrusion base because this is the main technology. And I also want to concentrate actually on the coarse filament printing as shown here on the right side. But before doing that, just let me address a little bit the different options we have here. You often see what is shown here on the left, that we print with pretty high resolution and produce quite filigrane geometries here with possibilities also here, for example, accommodate some installation, etc., and complex surface, let us say, geometry. And on the other hand, so here something in between, and then in this case, indeed, large filaments. And going from small filaments to large filaments, of course, you lose this resolution, but on the other hand, you are much faster in printing and producing some large structures. And what you also have here as a great benefit is that you can use normal size aggregates, so actually ready-mix concrete. And this is why I will address this topic today. So we feel that it's really the way to go for at least some applications of 3D printing. We can show here as one of the, let us say, benefits of this approach, specifically also the productivity. Deposition rate is shown here for different sizes of filaments, which you deposit for the same printing speed. We have tenfold and even more on volume, which we can deposit per time unit. Good. So we recognize this benefits and suggested already a couple of years ago an approach we called Conprint 3D. Conprint 3D stands for on-site monolithic 3D concrete printing. We offered this approach during Bauma in Munich. So this is the largest fair for construction machines worldwide. And we also were awarded Innovation Award. And the idea those days, it was not much an idea. So we haven't built a machine those days. It was just a concept, but the concept was pretty sound. And I will show you that nowadays it's also implementation, so that indeed we have some application of this concept in the practice of construction. So the first point in this concept was that we actually want to follow the requirements of today's architectural and structural design. And this implies sharp corners, straight geometry, massive cross-section. So we don't want to jump right away for something very filigree, which is not really kind of very much widespread to the market, but stick to what we actually require nowadays. On the other hand, we want to use to maximum extent the machinery which exists already, and we want to print on site and not in the fabric. And then another important point, we want to use ready-mix concrete, which spares costs and kind of a link to existing standards. So you see here some scheme as we started our thinking process, and you see also the first printed element in our lab. We have here a little video. I hope that it works. Yeah. So this was a presentation of this concept during the fair, and you see it's still quite a very schematic, but basically the most important points are shown here, so that it's a large scale, it's on site, it's using the existing mobile pumps. And then we follow this concept. So we built a large print head and install it first in our lab on a gantry system, as you see here. And you see that it's a little bit different than other type of printing. It's kind of a long bricks we deposit here, and we can also form sharp corners and produce kind of a similar geometry as for masonry. Good. So now, after showing the concept, I want to discuss with you a little bit what we need to successfully implement this concept in the practice of construction. And for this, we need, of course, a material which complies with the requirements, and I will address this right away. On the other hand, we need an appropriate machine. So I addressed this mobile pump as a base machine, but it's not all. We need, of course, also appropriate print head and maybe some other devices for steering the machine. And of course, we need also software for transferring the planning data in the data we need for the execution of this job on the construction site. So let me start with requirements to concrete. And obviously, we first need to deliver concrete from the let us say ready-mix track to the site as such. So we use this pump, and we need to pump the material to the print head. Then in the print head, material need to be extruded. So it should be extrudable. First, it need to be pumpable. And then extrudability implies that we have a particular deposition rate of the material, which is also arranged in the way that it complies with the printing speed of the and movement speed of this pump. And when material is deposited, we want, after a while, deposit another layer and another layer. And this is what we call buildability. So that material which is earlier deposited can carry the load of the subsequent layers of the material which come after. Good. And finally, when structure is printed, we of course also require some properties in the hardened state according to standards, and I will address this as well. So let me start with the pumpability. And here it's very important to understand that actually we have here a very complex process. And the complexity is defined, first of all, by heterogeneity of concrete. So when we push concrete in the pipe, we have some segregation. We have formation of thin lubrication layer here, as you see on the walls of the pipe. And actually, the properties of this lubrication layer define the resistance of concrete against moving in the pipe and also the energy we need to apply to let material move. So for this reason, we need actually characterize material, and then when we have these values, we can also predict what pressure we need to apply in the pipeline to achieve a particular flow rate in the pipe. And what we use in our work, and it's also pretty established already in the pumping industry, we use this kind of a device which we call sliding pipe rheometer or sliper short. It's kind of a little piece of a pipe which slides, and this mimics the movement of concrete in the pipe. You can find the details on this paper, which is cited here. And then we measure actually resistance to this sliding by installing a sensor here in the lower part of the device. And we can change here the weights, so the amount of weights we apply to the pipe, and we can change also the speed of the movement. So we can have a relationship between flow rate and the pressure from this experiment. And using this pretty simple formulas as shown here, we can find the constant A and B, which represents the rheological properties, viscosity, and yield stress of the lubricating layer. So, and actually this technology is already proved, so it works really very nicely. And this kind of a device can be used in the practice of construction very easily on the construction site. It's pretty robust and works very nicely. So it's a little bit more difficult if you go for characterization of extrudability, because the geometrical boundaries are here much more complicated. Usually we apply kind of a screw system here, and we can predict the flow of the material, the flow rate pretty well, depending on the speed of rotation of the screw. But what we cannot predict with some analytical approaches as yet is the energy we need to move the material with different viscosity or different rheological properties. So what we do to gain more insights, we go into numerical simulation. We use distinct element methods, which is very appropriate here. And you see from this simulation that we indeed also can look inside this kind of a print head and see some unsteadiness maybe in the flow or some concentration of forces. And this helps us to develop in a very focused manner new designs of the print head, but also maybe adjust the rheological properties of a material we want to print. So I have here also an example where different deposition rate is shown. Actually, the flow rate of the material is the same, but the print head moves with different velocity. And you see here what I mentioned before, that it's very important to adjust the deposition rate of the material to the speed of the movement of the print head. Good. So at the end of the day, what we can suggest that for every extruder which is attached to this kind of mobile pump or any other equipment you use in extrusion-based 3D printing, you best measure inline the energy which you need per unit, so volumetric unit or weight unit of concrete extruded. It's the first thing. Then you have this relationship, the extrusion rate and the energy needed for a specific device, but you also look on the quality of the concrete coming out of the nozzle. It should be a steady flow without any interruptions, etc. And then after the deposition, if you want to keep the shape of the nozzle, then we suggest to use this kind of a horizontal deposition, so with some knee here in the nozzle, so it helps. And then you can use this very simple analytical formula actually to predict when the material will flow or not. So here, tau is the dynamic yield stress of the concrete, which can be measured using rheological tools, so rheometry. And then other parameters here on the left, it's material density, acceleration of gravity, and the height of deposit layer. So if material is a little bit soft to keep the shape, it just flows until h is small enough so that this equation works, and then the flow stops. Good. You probably noticed that in our approach, we try to keep the shape actually of the nozzle so that we have a very good control about the shape of the element, since we also use pretty large filaments in the deposition. So this is an example from the lab. In this case, it's already about buildability. So we look what would be the limit when we place layer by layer material, and how well we can predict actually the failure of the material if the built-in process is pretty fast. And this is done here, of course, on purpose. So we want to see the failure so that we can actually check if the prediction works well. And there are two types of failure. Basically, on one hand, it can be material failure, so that the layers which are further down, so on the lower side, that they are kind of overloaded by the many layers which come after. So you see that actually the formula is very similar what I showed before. Just the difference is here that the height is here depending on the time. So the height is not the height of just one layer, but of all the layers which come here during the minutes and hours of the deposition. And of course, in time, the resistance of material will increase. So we know this concrete changes its rheological properties in time. We call it thixotropic behavior. And what you see here is extension of this term by thixotropy constant. And again, we have time here. So we can measure this development using different devices. So basically what we want to gain is this relationship between the static yield stress, which is shown here, and the age of the material after the deposition. And in the first hour or 1.5 hours, it's mostly linear relationship, which is of course good. But then due to hydration, it becomes non-linear in most of the cases, strongly non-linear, and then we need to use non-linear relationship if we go that far. But usually we stay here somewhere in this region. And then important point is to mention that we need to go here to different type of rheometry as we usually do by characterizing flowable concrete, because in this case, the concrete is already not flowable at all. Or if it flows really very, very slowly under pressure. So we usually recommend here to use penetration tests like this, or this kind of compressive test either on a separate material or on the what of course more practical to have some here pressure on the deposited layers. Good. Again, I cannot go here in much detail, but if you are interested to get more information on testing as such, you can read this paper, which is published in Cement and Concrete Research. Well, and then, as said, one possible scenario for the failure is the material overload. But on the other hand, since we work often with slender elements in 3D printing, we might have also stability failure, as you see here. So you see on the long segment of the wall, there's some stability issue pretty pronounced. And this doesn't occur in some other situation when we have here corners where the situation is much more stable. So for simple elements like this kind of a wall, there are analytical formula you can use, but for more complex situation where you have really here shapes which cannot be translated easily into analytical formula, then we recommend to use finite element analysis. Good. Now I come briefly to material design. Actually, it's not kind of a rocket science, but first of all, we need, of course, to attain these rheological properties, which I mentioned. And when we go to a real concrete, so ready-mix concrete, we recommend to follow the approach by Andreasen and Andersen, which sometimes also called Fuller form or curve. It's the similar approaches, which enable us to get maximum density packing. And how to get it? You probably all know this. It's about choosing the ingredients for the mixture in the way so that by applying some quantity of these different materials, and actually we start already with cement, not just with aggregate cement, and then in this case some pretty fine powder, so stone powder here, so limestone powder, etc. And then we have two different sands, and then we go to larger aggregates. Good. You see that in this case, we could match the shape of the curve pretty nicely. And this is what we recommend also to everybody. In this case, we indeed can minimize the cement content, but still keeping good extrudibility, pumpability, and on the other hand, also buildability. So again, you see some examples here. And what we also use some amount of super plasticizer, so just again to achieve the rheological properties as required. So now very briefly to hardened concrete. So when we printed material, after a while it hardens, and of course we need to know what properties we achieved. And in this case, it's really important to figure out in which direction we need to test. Basically, we have here some heterogeneity and anisotropy due to the joints, as you see here. So the joints are usually a little bit weaker than the rest of the materials, the bulk material. And if you have many filaments deposited one aside the other, you might also need to take specimen in this direction. In this case, two directions are fine. So it's the direction of printing would be direction U as shown here, and direction W, right? So for these two directions, I'll show you some results. And I compare for the same material, but cast in the mold. And you see that we have here a little bit difference in the performance with respect to compressive strength on this example. So it mustn't be always the case, but in this case, a little bit smaller due obviously to compaction. So obviously in the print head, we do not have the same degree of compaction, but maybe also there's some minor effect of the joint as well. For flexure, we have for these two directions even a little bit higher values, but in the direction of the loading parallel to the joints, we have some decrease in the flexural strength, splitting more or less the same. And most pronounced, of course, is the difference in the direct tension. So this is tensile strength. And you see that when we test it's perpendicular to the joint, so in this direction is tension, then the values are much lower than in the case of the cast specimen or the specimen which is printed but tested in the perpendicular direction. So it still might be enough value, which good enough, but this is what you should know. And if it's of interest to have the strength, specifically also tensile strength in different direction, then it need be tested. And you see already that actually the amount of testing is increasing in comparison to what we have usually concrete construction where we cast it into the mold. Let me say a few words about the print head. You see that print head consists here of different portions. So in our approach, we use here kind of a reservoir as a buffer. And then we have here a possibility also to vibrate concrete a little bit in this reservoir so that it flows better into the screw extruder, and screw extruder delivers it to the here shaping elements which can also make the filament a little bit wider or narrow, and we can also change the height of the filaments. A very important point is that given the large size of these mobile pumps, you can imagine, and probably you know it from your own practice, that it's pretty soft. So at the end here of the pipe where the concrete is delivered, it's quite a large movement of the pipe due to the pumping process itself, but also due to wind, etc. So it's there need to adjust actually the position of the print head. And this is the approach we suggested here, to have some adapters which enable to compensate the movement actually of this mast. And the final here point, just to close the loop, I mentioned that we need machine, but we need also the processes and data handling. And here, just a schematic presentation how it works. So we work, for example, with CAD and beam data. This data need to be translated to slicing data for individual layers. To achieve this, we need kind of a translation program. And then after it's sliced and translated in the code for the machine, so it's a second translator, then it can be printed. And of course, we need also feedback, what is built, what is planned. And this is what we are working now quite intensively to collect information during printing by laser sensor concerning the geometry of individual filaments, but also using photogrammetry to collect the data of the printed structure. And we also induce some sensors to collect even more information, for example, on the temperature and other parameters, ultrasonic measurement, etc. So now I come to the promised implementation of this approach in the practice. So we collaborate with the firma Putzmeister, which is a German producer of concrete pumps. And this company learned about our approach and liked this approach and implemented this approach. Actually, this presentation was last year in the same fair in Munich, where we got our award a couple of years ago. So after 6 years of working on this, they presented the machine. And this is some data. You see quite a good outreach of the machine. So the layer width can be up to 30 centimeters, layer height 6 centimeters. The print head is not very fast at the moment, but they are working on increasing the speed. And there are some other parameters. So basically what you see here in this box, kind of a hidden, is also some adjustment. So this system to adjust the position of the print head, but they don't want to show it, of course. And so sorry, it's loud. So this is the recent video of printing. This was the first commercial structure printed here in Germany, near Stuttgart. It was for Züblin company. And you see, of course, here, so a little bit material testing. So this is just to see if we are kind of in the range of expected. And you see how it works. So it's deposits layer by layer, pretty wide. And after a while, the complete building is built. You see here also delivery of concrete. So it works in the usual way, as if you would pump this material just in the formwork. But in this case, it's not placed in the formwork, but it's deposited layer by layer. And this is what we call 3D printing. So this is what was produced. So it's nothing huge, but it's considerable geometry already. It's 6 by 10 meters in a projection, and height of 4 meters approximately. Good. There are some advantages. It can be here set up on the construction site pretty fast. The material is pretty cheap in comparison to some other materials which is offered for 3D printing. And then the printing process itself is pretty fast, and then set down of the procedure is also pretty speedy. Finally, I have 2 or 3 slides with respect to reinforcement because we need this for many applications. And this is what we suggested recently for this specific technology. In the first option, we talk about partial automation by overprinting of the attached reinforcement mats. It means we first print the core here without reinforcement, but we place some here rods of reinforcement to carry the mats. And what you see here, actually on the external part, there are mats which we then overprint. The second approach is that we first place reinforcement cage, and in the middle we have some little mesh just to control the material flow, and then we print from one side and from other side and close this, let us say, cage from both sides so that we have a monolithic structure. And then the third option, we simultaneously position here reinforcement and then actually envelop this reinforcement from both sides with concrete. So you expect, of course, that the third option is the most complicated to materialize. Some little picture here. I see that the time is running, and probably I need to stop my presentation very, very soon. But you see here once again how it works. So first printing of the core, then position of the mats, and then overprinting. This is how we position here actually this little pieces of reinforcement which look out of the printing structure. So we have also developed a little machine for that. And then you see how it looks after overprinting. So then some images for this positioning from the side. It's again all on the lab scale at the moment. And finally, you see here a schematic presentation of the machine for automatic positioning of reinforcement. It's well together here to a mesh, and then we developed a print head which enables to envelop this a mesh from both sides. Finally, I want to advertise a conference which is here in Dresden in September. If you are interested in fiber reinforced concrete, you are welcome to come to BFIP 2024. And this is all for today from my side. So thank you so much for listening. And of course, I will be happy to answer any questions.
Thank you for your presentation. And now we want to move on to the short Q&A, but I'm so sorry because the time is so limited. So could you move on to the next presenter without any Q&A? And I will pick up some questions on the panel discussion. So but anyway, thank you for your valuable presentation, Professor Victor Mechelin. And now, so I would like to introduce the next presenter, Professor Minoru Kunieda. Okay. Okay. So firstly, I would like to briefly introduce Professor Kunieda. He is a professor at Department of Civil Engineering, Guelph University, and he received his Doctor of Engineering from Guelph University in 1999. And his research interests are in high-performance fiber-reinforced concrete, repair and retrofitting for concrete structures, 3D concrete printing. Especially, he is focusing on fairer behavior of printed member by 3D printer at present. And he was a member of JCI Research Committee on 3D concrete printing. He is also a secretary of JSC Committee on Guideline of Design Construction for Formwork by means of 3D concrete printing. He is a vice chair of JSC Committee on Guideline of Design Construction for very high strength fiber reinforced concrete. So today, he will deliver a lecture entitled Introduction of Applications in Japan and Feasibility Study on 3D Concrete Printing. So, Professor Kunieda, please share your slide. And please start your presentation when you are ready.
Can you hear me? Okay.
Yes, please.
Okay. Thank you for your introduction, and it's my great honor to have a presentation today. Today's my talk is introduction of applications in Japan and feasibility study on 3D concrete printing. Okay. So first of all, I would like to introduce some applications in Japan by a Japanese colleague. And for the background and motivation to use the 3D concrete printing, Professor Victor has already introduced in terms of the many aspects. So today I would like to show you some specific topics and feasibility studies in my lab. Okay, I will show you some applications in Japan, and this is provided by the Aizawa Corporation. You may know these photos, the small house for the toilet, and this is a bench printed by the 3D concrete printer, and very how can I say interesting topology, and in the plan and the design is conducted by the student, the University of Tokyo, and now they are used in the station in JR East. And this is nice photo and nice facade of the architecture and the wall. And this is also a nice facade by the lighting, and the 3D concrete printing texture is well used in this building. And you may know this photo, and this is provided by the Obayashi Corporation, and this is a bench, a huge bench. And in this case, the formwork is printed by the concrete printer, 3D printers, and the inside of the member is casted by the UHP-FRC. And this is nice architecture, small house. How can I say the usage of this building? But this is also the formwork is printed, but the inside or core member is casted by using the UHP-FRC. And this is the bridge by using the techniques of the topological optimization. And you know that this is just a bridge, a precast bridge by Taisei Corporation. And this is the recent trial by the Taisei Corporation. As you can see, in the foundation is very complex shape. So they measured the shape, 3D shape of the foundation, and then they print considering this gap. And as you can see, this is nice printed structures is possible. Probably they try to use in the tunnel structures. So the next application is provided by the Shimizu Corporation. As you can see, this is also the homework for the huge buildings. And you can see the homework was printed by 3D printers. And then, sorry, and this is the precast members. So they construct on site and then cast the ready-mix concrete inside of the formwork. And they also build huge gantry type 3D printers, and they made these kind of the wall structures by 3D concrete printing. So in Japan now, many companies and researchers try to use the 3D concrete printing technologies. And today, I would like to show you some feasibility studies related to the batching and mixing works in the 3D concrete printing. This is just one component of the 3D concrete printing technology. And the second aspect is we confirm the buildability during the manufacturing process. And also we try to know the failure process of the printed members in flexure. So I will show you some these three topics briefly. So as you know, we can see the many figures and videos for printing process. But before that, most printing and printer use the mixing and in addition to the batching, right? And but unfortunately, the ordinary mixing and quality control, such as slump flow measuring, have been adapted. And in this case, advantages of 3D concrete printing may be lost because of much work are needed during the mixing process. And in addition to that, the repair and the strengthening are expected to be a large market in the future. So it's difficult to make only precast members is not so measured and not common. So we have to enhance not the precast, but on-site casting presented in the Victor presentation. And after that, for the safety on-site is one of the key issues nowadays. So we have to insert the automated casting of concrete should be used and may be useful for the recovery of disaster damage. So we try to develop the on-site shot printer covering that issues as I showed before. So the key technology is the spraying techniques that has been already used in the tunneling method. And the powder and the liquid, including emulsion, were pumped separately to the mixing nozzle. And then those material has been well mixed within the nozzle. And then well mixed mortar has been sprayed to the target. That is, so no batching and mixing process are not necessary. through that techniques, the compressive strength is very easy to gain. So this is the compressive strength, relationship between the compressive strength and tested edges. And after 1 month, 60 megapascal is obtained. So compressive strength is enough to use as a structural members. And interlayer, which is significantly observed in the extrusion printer, is not existing. I mean that more homogeneous material has been obtained. And of course, this spraying techniques can be combined with the ordinary industrial robot. But this is just optional, but we try to combine with ICT backhaul. Nowadays, ICT backhaul can be, the movement of the ICT backhaul can be programmed. And in these videos, the operator does not work, just sitting. So the backhaul is automatically moved as programmed. Of course, we try to use these techniques combined with ICT backhaul. That trial printing was done for simplified members because this backhaul is, of course, programmed, but not appropriate for the complex members and shapes. So first one is just wall with straight shape, and the height is 1 meter and the length was 5 meters, and spring direction is vertical, as you can see. And the duration for the printing is only the 60 minutes. And we also try to use these techniques to the concrete formwork, for the column. But unfortunately, behind the reinforcement, we need a mesh to catch the spray material. So this is not so appropriate in addition to the surface treatment. And so this is just more different shapes of the wall structures. And we can program this shape, and then spraying techniques can be applied. And this is nice shape, except for just a surface treatment. And to improve the surface roughness, we also prepare this kind of machine to do the throwing on the surface. But up to now, this is just under developing, and we need more innovation to obtain the smooth surface. And this is just ordinary extrusion 3D printing. And in Gifu University, we made the consortium made by the 5 companies. And now we try to do the developing of the existing structures and also the research work. So in our system, we use the nozzle to provide the quick setting agent just next to the nozzle for the material, because in ordinary system, sometimes the quick setting agent has been mixed with the mortar already, or added just before the nozzle. But we might have some risks for the pumping, so we just sprayed to the filament directly. And using this system, we try to measure the deformation of the printed members during the manufacturing process. because we should know the buildability of this printing system. So in our lab, we attached the laser displacement transducer to the nozzle, and then measured the distance between the filament and this transducers. As you can see, the zero value is equal to the design value. This is just a target for the printing, but the negative value indicate the lower than design value due to the sink of the printed layer. So we concerned the sink of the printed layer. So we measured this distance between the all printing paths. So this is just the result of the measurement. And this wall structure is made using a mortar with a flow value of 150 millimeter. This is the appropriated material at this time. So I show the three graphics. This is the result of the bottom face and the middle bottom part and the middle part on the top of the wall printing. In the initially, the measurement result value shows almost zero, but after the 3 layers, my negative value was observed because in this phase, the above layer are pushed to the bottom layers, and the bottom layers has lateral movement from the original positions, because we have the interface between the steel plate and each filament. So the friction or deformation due to the pushing has been observed here. But in the middle part or top part, no change has been observed. But finally, the negative value has been improved to be the zero, because no loading from the above layer in the top of the walls we can see. And this is a result of the wall with the mortar flow value of the 140, a more stiff mortar case. And in the initial part, we observed the same behavior, even if the stiff mortar case. But as you can see, the stiff mortar, no deformation was observed to be the top of the wall. And then in the mortar flow value of the 160 millimeter case, the movement of the lateral direction was observed in the bottom layers, in addition to the deformation due to the compression of the by the above layer weight. So finally, we have the collapsed members at the 22nd layers. And I will show you the third topics on the flexure failure behavior of reinforced printed beams. And we made the beam specimen using that 3D printers. And the printed mortar having the water to binder ratio is 32.2%. And additive with fly ash has been used for the mix. And beam size, the length of the 2,150, and height is 195, and width is 96 millimeter. And specimen has a reinforcement and without reinforcement. And in the case of the reinforcement with reinforcement case, we terminate the printing after 3 layers, and we put the reinforcement by manual, and then we also print continuously. And as I said, the sodium silicate solution was sprayed for each filament. And this is just material properties of the printed mortar. This is a mold value of the mortar, 86 megapascal, and the yield strength of the reinforcement is 392 megapascal. So this is just result of the flexure strength obtained from the beams without reinforcement. We observed the flexure cracks, single cracks, within the moment constant span, and the flexure strength was 3.7 Newton per square millimeter. And this is just a cross-sectional photo, and we can see the white line was observed, right? And this is the sprayed sodium silicate layer, but up to now the effect of this layer is not significant for the mechanical response of the beams. And this is the relationship between the load and displacement with a beam, of the beam with reinforcement. As you can see, we can obtain the ordinary response of the reinforced concrete, and after the initial cracking and the yielding of the reinforcement and the compression failure. And the estimated capacity of this beam is 10 kilonewton. So well estimated. And we also checked the compensation plane during the loading, and we put the strain gauges to each filament, and then we checked the strain for each layer. And before cracking, right, the straight line in the strain was observed, and the first layer has cracked, still straight, and second layer has cracking, and third layer has cracking, and fourth layer has been cracking. We observed the compensation plane. And in the final stage, even if includes the delamination of the layers, we have the straight line within the members. So during this is just crack patterns of RC members, and as you can see, the flexure cracks has been occurred initially, and then number of cracks has been increased in some cases, and after that, the delamination along the river has been occurred. And fortunately, in this series, this crack pattern affects not significantly to the capacity of the loading, as you can see in the load displacement relationship. But in some cases or in the future, we have to concern that delamination of interlayer may be affecting the compressive failure in addition to the bond behavior of the members. So we should concern the crack patterns within the printed members, or hopefully we should control the crack pattern within the same conditions. So this is just information on the compressive strain at the top layer. As you can see, we have the over 2,500 micron or more in the final stage sometimes not reach to the 3,000 because maybe that we have the delamination of the interlayer at the top layer. And we also check the interlayer bond strength at the bottom layer and the top layer of the beams. And as you can see, the bond strength of the top layer is 1.37, but the bottom layer is 1.68. The lower layer is provide a higher bond strength at the interlayers. Because of the, as you can imagine that lower layer is loaded by the weight of the upper layer, so good bonding can be obtained. And in the beams under flexure, delamination at the compression zone may reduce the ultimate load. And we can imagine that. In addition, weak bond strength induces a splitting crack by ring tension of the lever, around the lever. So we should improve the interlayer properties when we use as a structure members. So I would like to conclude my presentation, and it is necessary to reduce the amount of the work required for the batching and mixing to enhance the advantage of 3D printing. So dry spraying method is one of the effective methods for this purpose. And measuring the position of the filament during the additive manufacturing process is useful for understanding the behavior of printed members, namely the buildability. And understanding the failure process of the printed members is important and necessary for the structural applications. And this right photo shows the crack pattern in the shear failure. Of course, even if the shear failure case, the crack pattern is very complex, sometimes belonging to the interlayer of the printed layer. So we should have the much back data related to the fracture process of the concrete members. So, so this is just provided by Shimizu Corporation, and this is the image of the present construction site for the bridge. And there are many tools and machine in the construction site. And in the 2030, some part has been changed to use the drone or the robot and the precast system, something like that. But 2050, the remote work has been dominant to control the machine in the construction site. And finally, I would like to inform you that JSC guideline for design, production, and construction of the structures with 3D printed formworks has been developed now, chaired by the Professor Ishida, the University of Tokyo. And I also contribute to that works. And probably and hopefully it will be coming soon. So please refer or see this document and I hope that this should be helpful for your work. Thank you for your kind attention.
Thank you so much for your nice presentation, Professor Kunieda. And now we move. I would like to move to the panel discussion by skipping the short Q&A because I would like to have much time to discussion. So now we continue to welcome Professor Mishrin and Professor Kunieda as panelists. I will also be moderating this panel discussion. From today's lecture, we can see various attempts at applying 3D concrete printing. These techniques are still developing and hold significant potential. However, I understand there are also some challenges in their application. So to extend it, 3D concrete printing technologies, we need to focus on specific targets to progress effectively. And from the audience, several questions regarding the boundary between the filament and the bonding of each filament. So it depends on, of course, it depends on the application of the structure. But I would like to ask some question about I'd like to ask the panelists this question, and then sorry, I didn't share my screen. This one. So this question: what should we make by using 3D concrete printing technologies? And regarding it, what specific technologies are necessary to develop? I believe there are several aspects to consider, such as structure use when the structure usage is considered, reinforcement, the composite materials, or something. And of course, we need to consider the durability and of course the cost. So firstly, I would like to ask to Professor Michelin, could you please share your thoughts?
So I'm not sure where to start. I mean, this is quite a series of questions. So can you indicate where I should start? Is it about more durability or about target applications? Or maybe I just haven't got the key.
Yes. So from your presentation,
now I see the question. Sorry. So now I see the question here on the screen. So I missed it.
Okay.
Yeah. What should we make by using? So I mean, you mean what we should produce, right? Yeah. Well, let us maybe start with the question what we want to produce. And of course, the first thing we see in the examples of application, there are walls, right? And I would say there are no problem to produce walls, both monolithic walls and also walls which we say, okay, we print kind of a formwork and then fill this formwork with some more or less conventional concrete. So this is not a problem. What I feel we need to do in the case it's formwork, kind of a printed formwork, that it's not lost but integrated, because sometimes we use the term lost formwork. And indeed, if you do not consider this formwork with respect to design, so load carrying capacity and durability, performance, then it's kind of lost. But if we consider this integrated formwork, both with respect to durability and load carrying capacity, then it's a good part of the story. And my feeling is that it should be the first step towards using this technology more efficiently. So to find a way really to consider this performance of the formwork and the design, because this is most widely used actually approach with respect to the walls. So the next point is columns. So we can print columns, but then we need a concrete which develops buildability pretty fast. So here, in this case, we need to have what we call 2K mixes. It means we add some accelerators or whatever we use to speed up the process of structural build-up in concrete. So, but now I look at your at your questions, and maybe for these 2 points, I also to address costs and durability. So costs, with respect to the costs, I would say ready-mix concrete, of course, much less expensive than some pre-mixed concrete, which cost manifold. And this is what we suggest to be the primary approach. And it can be spraying. Then it's not really ready mix, but I believe it can be done as real concrete with larger aggregates. With respect to durability, and I believe this is a question also among here the Q&A. So if these interlayers affect durability, yes, they can, but it doesn't mean that we cannot do anything against this. So it's all about also shaping the properties of the interlayer. So it depends on the rheology, it depends on the pressure of the tools we apply. It depends also on the treatment. So usually we actually face problems when the time intervals between the layers are large, and in this case we can apply some treatments or some interlayer material so to improve the bond. Good. So, and maybe not to make it too long, the answer, if we move to horizontal members, right? Then there are different strategies. So it can be done in the way as Professor Kuneda shown, that we print a beam. The question is, of course, if it's kind of cost efficient or not. But another possibility, if we have, let us say, members with high resolution, that we actually print in height and then turn it and make so the direction of actually building it in the structure perpendicular to what we actually used as a printing direction. And this is used for production of all kinds of the elements, for example, for bridges, etc., which we span then together, and then we can use these elements as kind of horizontal elements. So but this is all done actually not in situ in most of the cases, but in the fabric, so kind of a precast or preprint plant, and then need to be mounted on the construction site. So in this case, we also need to consider these 2 approaches. So what we can produce on site and what we can produce in the pre-print plant. So maybe for the beginning, it's my answer already pretty long.
And thanks, Arnold. And so from your presentations, you introduce reinforcement with concrete 3D printing. So what's the purpose of you have several menu of introducing the reinforcement. Of course, I understand the techniques is undergoing, but what is the best way to introduce reinforcement with concrete 3D printing? Do you have a...
Yeah, thank you so much. It's a very good question, and I'm not sure I can tell which is really the best way. In the situation which, let us say, offers pretty simple geometry, then we should also go to a pretty, let us say, straightforward method of reinforcement, and maybe method 1 or 2 is the best option. So with method 2 and 3, we have more flexibility, but method 3 is most complicated. So we need really very elaborate print head with this equipment for producing also some joints for reinforcement, and we need also delivery system for the pieces of reinforcement, etc. So it's the question if this complexity of the process is also feasible under practical conditions or on site. And so I'm sorry, but I cannot really answer the question, what is the best way? What we try to show that it's feasible to implement steel reinforcement, because this is, I believe, I mean, to implement it in a different way as it's commonly used in most of the cases, that you just produce formwork and then everything else occurs actually in the standard manner. So you place reinforcement in and then you pour concrete. So this is a good approach in many cases, but if we say we want to go further and integrate reinforcement better in the printing process, then this is a free approaches which I showed. And actually we tried to estimate the economic, let us say, part of the story, but you know, to estimate this economic dimension, we need reliable data, and for reliable data we need a kind of already existing process with specific parameters, etc. At the moment we are at the lab stage of the development. We have some setup in the lab, and of course it's has not that much to do with what happens really on the construction side. And what we learn at the moment on the construction side, that it's still pretty much manual work to support the printing process, because the technology is not self-adaptive. And what Professor Kuneda addressed, that we have some deviation in the height and others. So we need actually a closed loop, so that system reacts on this and also reacts on the change it may be in the rheology. But we are not that far yet. And of course, if you introduce reinforcement, then complexity increases. Then we need to have even better command of the concrete floor to enclose reinforcement to have a good bond. So it's work in progress. So I cannot give you really a better answer at the moment.
Thank you so much. So, Professor Kuneda, so in your presentation, you showed the application of the repair of the structures. So, what do you think about what is your opinion about this question? So I mean, what should we make by using the concrete printing technologies?
Yes, thank you for your questions. Maybe we can apply the spring techniques to the repaired part, and the material property is enough as a repair material. But unfortunately, we have to make the closed loop to adjust the damaged concrete shape as introduced in the Taisei Corporation applications. So we have to measure the three-dimensional shape of the deteriorated concrete, or of course removed the deteriorated concrete part, and then we should spray just the design shape. So we have to develop the closed loop system, not only the printed or spraying techniques. It's not enough, right? Okay.
Oh, thank you. So my image from your presentation, the application for the repair is almost completed the other technologies. So do you have any real application on the real side? Of course, in your presentation, the construction site, the photograph of construction sites are shown. But so do you have other application site in Japan?
Of course, we can apply. Of course, if we success the system, we can apply to the repair of the deck slab and the column and the other structural members with reinforcement. But anyway, before that, we have to print to the adjust size, right?
Okay, I understand. Okay, so let's move on to the next question from this discussion. I would like to ask about when we apply the 3D concrete printing to the structure member, how do we to decide to have a regulation, a specification of design for safety? Of course, this technology is not so applicable to the structure member, but in the future, if we use the 3D concrete printing for the structure member, we have to consider the different way we have to consider the different manner of the design. So what kind of problem or the issue we have to consider if we use the concrete 3D printing to the structure member? Do you have some comment or some thought? Okay, so please, Professor Michelin, do you have?
Thank you. I may start with a comment that we have at the moment some options to choose in which design framework we want actually to act, because there are no, at least not in Germany, no code for 3D printing structures. We can decide if we go here for maybe even code for masonry, right? So we can use actually a design code for masonry, and then we need, of course, to test the properties of the print material in the way that we also get the input value for this design. But then we have also a possibility to design for non-reinforced concrete walls, right? This is a specific again design, and then if we go for this design, we need to measure the properties which we use in this design. And finally, of course, we have also design of reinforced concrete walls or not walls, and then we of course need to test in a proper manner. And this is kind of a very general thought. But then when you go for specific design, then you are bound to also the framework of testing methods. I mean, for example, if you work with a concrete design, so with structural concrete design rules, you should test on the specimen which are defined in appropriate regulations, right? You cannot go to a mortar scale or to anything else, right? And this is what we should consider. And then what I mentioned before, the difficulty is that we need to consider to some extent at least the anisotropy of the structure, which increases the number of tests needed. But this is always to the designer to define how much effect he actually expects from these different directions. For some designs, it may be not really crucial, and in some design, they might be very sensitive to that. Finally, we should, of course, consider that it's not just about the load carrying capacity, but it's also about durability. And in this case, again, so major concerns are interlayer quality, and it doesn't need to be bad, but it needs to be tested, and it needs to be tested separately. Just to give you a flavor of complexity we get, so usually we say that aggressive agents propagate into concrete kind of in a uniform front. But when we assume that the quality of the interlayer is different, and it's kind of a spot where the progress is faster, then we need to rethink actually our approaches to durability design. So it's, I would say work in progress. What I can report that in RILEM, this is International Union for Testing Concrete and Concrete Structure. So in RILEM, we have a committee where we consider how to actually characterize concrete in hardened state, specifically, since we are talking here about the design, this is what is needed. And we will, as a result of our work, make some suggestion for kind of recommendations for practitioners. But it's not done yet, so it's work in progress.
Thank you very much. So how about, what do you think about this, Professor Kunieda? And I would like to know your last slide, you should introduce the JC guideline about 3D printed printing as the usage of the format. And I also would like to know the how to design how to design of the structure with 3D printed format. And please give us your thought.
First of all, as Victor said, the best way is to make the concrete printer providing the homogeneous material or homogeneous members. But maybe it's difficult, so we can make the design code considering the heterogeneity within the members. But we need much data related to the failure process, including the crack patterns or the technologies to estimate the cracking due to the subjected to the loading. So in the guideline and up to now, we have to use the material properties with the safety side, and I mean the weakest values or weakest directional values can be used as a design. Of course, this time major usage is the formwork as a non-structural members. So just a very not so high performance is not required. But in the future, we have to prepare or either way to develop the homogeneous printing techniques or the guideline considering the heterogeneity.
Thank you so much. Okay, so we have much time to discuss. So let's move on to the different topics not shown here. I would like to know the use of the other materials for concrete 3D printing. So for example, the fiber reinforced cementitious materials or the other, can I say, the reinforcement, for example, the FRP rod or FRP sheet or some other the reinforcement materials. So do you have any trial to use fiber reinforced materials or the other, for example, FRP materials? So could you provide us some thoughts?
Absolutely, absolutely.
Yeah. Yes. Yes.
Absolutely. Thank you for asking. Actually, introducing reinforcement as fiber reinforcement, it's quite a straightforward way. So we can mix fiber then we can print fiber reinforced concrete. So it's has been done in many places. So we also focus on this. We can print also with strain hardened cement-based composites, which provide a really kind of a structural performance. So it works very nicely. Also, the example shown by Professor Koinada, where we have some supports for the bridge, it was also done with this technology, strain hardened cement-based composite. So it's pretty powerful. So short fiber, no problem at all. Well, of course, we need to adjust a little bit printing so that fiber doesn't stick in the print head. So it's kind of a good flow of the material, but it's not a problem as such. We also introduced actually a lawn fiber, so in different form. So what we really like as a technology, it was developed in my group, that we impregnate carbon fiber, so carbon yarns with very fine mineral-based suspension. And then we either deposit these yarns between the layers or introduce them directly into the filaments. So in this case, we have a reinforcement, but it mostly, of course, in the direction of the printing. So what we still are working on introducing additional reinforcement layer perpendicular direction. Here we need a little bit to adjust the deposition technique, but it's feasible from our perspective. So working with long and short fibers seems to us a very good option. And specifically when I come back to this technique where we impregnate the fiber just before integrating it into the printing process, we are very flexible. So we can follow any shape. And this seems to be a very problem. I couldn't include it in my presentation, but maybe when you invite me next time, I will be happy to present that.
Thank you very much. So could you provide me the other aspects or some other comments, Professor Kunieda?
Yes, thank you. Our group does not have the activities to arrange the reinforcement, FRP or CFRP or other short fibers, because one of the reasons is the cost of the printed members and materials. So we only use the ordinary mortar or close to the ordinary mortar and ordinary rebar. But I think we can enhance the advantages of the 3D concrete printing when we use when we make the thin members. And in that case, the critical issue is the durability of the reinforcement when we use the rebar. Maybe the no corroded or FRP can be useful for that case. So we can try to do the investigation using FRP or other reinforcements. Thank you.
If I may add just one sentence, this thin members, it's indeed the key word here. So for thin members, it makes a lot of sense. Professor Kunieda also presented an example from the Shimso Corporation, where the integrated formwork was actually made in the plant and then transported to the construction site, mounted, and then well, it was a very nice formwork built of this and then poured. So, and here fiber reinforcement has few advantages. First, it's about transport. So you need some reinforcement to transport these thin, large members. Then for mounting, you need reinforcement again. And then you have a casting pressure, right? So then you need also reinforcements to take the tensile forces which come with the casting. And what I really want to emphasize, this kind of a skin which we have in these columns, so it's perfect for durability. So this is kind of an internal skin which protects the core very, very nicely. So, and actually I also believe that it also improves to some extent the load carrying capacity also in case of earthquakes, specifically also for this complex geometry used there. So in this case, really the fiber reinforcement has many advantages. Yeah, I wanted just to add this information to the answer by Professor Kuneda.
Thank you very much. So now the time has passed, and I'd like to close this webinar. And thank you for the fruitful discussion. I believe it was very impressive to the audiences, and the knowledge and insights shared today will be valuable in advancing of the study of 3D concrete printing. And it was also beneficial in challenging our understanding of this research field. But anyway, thank you very much for today's webinar, joining today's webinar. And I would like to express my gratitude to the invited lecturer, Professor Michelin and Professor Kuneda. Thank you very much.
Thank you.
Thank you very much. So let me close the webinar. This is the 7th webinar, and we are planning to hold to the next webinar in March or April next year, but the details have not been decided. So we will announce the detailed information once it is finalized. I look forward to seeing you at the next webinar again. And thank you so much for joining today's webinar. See you soon. Thank you very much.